Good. So where we left off yesterday was on the discussion of block diagrams. We started our lecture on block diagrams, on modeling, just as a reminder of why we do what we do and how the sort of engineering design process is. And then we saw that one of the tools for us to sort of draw out systems was using something called a block diagram. Well, today we're going to, and of course, the block diagrams have basically just a couple of elements to them. We didn't officially sort of go through that yesterday, but at this point, maybe well, really a lot of stuff to learn, right? So the first thing is that um, the block diagrams have rectangles, right? Then they have junctions, which you will see like that, where two lines intersect and there's a dot. And then they have these things, which are summing junctions, right? There may be more than one in it, and there are signs coming in to the summing junctions. So plenty of things you have to remember, right? You have to remember a rectangle. You have to remember where two or more lines cross on a dot in the middle called a junction. And then you have to remember these things called summing junctions. You sometimes see them like MATLAB has the summing junction looking like this with a little X in the middle, right? Some textbooks even have it like this just to make sure you understand. It puts a capital sigma, which is like shorthand for summation. Okay, the important thing with the summing junction always though to watch the arrows that enter the summing junction, what sign is on the arrow. So most systems are not the simple sort of two block systems that we looked at yesterday when we introduced this. Most of systems, I mean, if you think about it, like a simple power supply, for argument's sake, if I were to block out the power supply, which we did very early on, you remember you have the rectifier section, then you have the filter section, then you have the regulator section, and then you have the protection. So each of them in a power supply basically already have four blocks, and each of them has their own almost distinct behavior. You could make them separately. So the rectifier section, you will deal with just the diodes and the transformer and maybe any fuses and the like. The filter section, you have that big filter capacitor to deal with. The regulator section, which is all of the electronics that we spoke about, and then the protection section, which will be the various, the overcurrent and short circuit protection that we dealt with, and we looked at two of them. Plus you can also put additional fuses inside. And here, of course, in this section will also be if you have a variable supply, how you vary it and the like. And there's some feedback in this section that takes place too. The regulator works with feedback. We saw that. Okay, so you can see just even as simple as relatively simple speaking as a power supply, a normal sort of desktop power supply, that you have more than just a couple, one or two blocks inside of there. An amplifier would be similar. So as you get into more control systems later on the like, you will see diagrams and block diagrams get significantly more complicated than what we encountered. So the issue now is that if you encounter something that is a little more complex, not every one of them you're able to solve with a computer. Sometimes you may not even have access to a computer, and you have to really sort of sit down and pencil it out a little bit to get an idea. It might be quicker than trying to code something. So once you enter something and you land up with something reasonably complex like what we have here on the screen, how do you go about simplifying this? Right, well, the first thing is that every time you're given a big diagram, a big block diagram containing multiple blocks, the H blocks and the G blocks and so on, and we said generally, not 100% all the time, but generally the forward blocks usually have the symbol G. So G1, G2, G3 are the blocks that go from input towards the output. And the feedback blocks in almost all applications, not always and in not all textbooks, so you have to look at it, the feedback blocks use the symbol H, H1, H2, etc. All right? But always look at the diagram carefully to see if it is so before you make an assumption. That's point one. The second point is that we already know that from yesterday and from a number of instances before, that if we can get something looking like this, minus plus, sorry, let me put a block here. So G and H, right? So this is the output, this is the input here, X, Y. This is the feedback block coming here. We know that this two block arrangement with negative feedback, we know once we get that, that is G over 1 plus GH, right? We also know that if it happens, if that is a positive, then the sign below is a negative, right? So depending on this sign, the two block arrangement with feedback is always going to give you a G over 1 plus GH. So the rule in simplifying any block diagram that you are presented with is always to see if I can manipulate shifting the summing junctions and these takeoff points, if I can move them around so that I get left, every time I shift them, I get left with a G over 1 plus GH, a feedback block. Fair enough? And let me know if you're not hearing me, and of course, if you have any questions. And of course, you have to be able to read the things on your head. So if you look at this, for instance, here, you look at this, for instance, this is almost a feedback block, right? It's upside down. So instead of H coming on the bottom, it's on the top. But this is exactly what we did, a G over 1 plus GH, except that we have, right, except that we have this to deal with. That's messing up the works for us here. Similarly, we are almost good with this one here, except that we have some other little things that look like they're gumming up the works. We need to figure out what to do with those two things there, right? Fair enough? So this is where the simplification process comes about. So the first thing we need to know how to do is how to move what happens when you move a takeoff point. So if I have a takeoff point, this takeoff point is after. So X is coming into block H, and out of it is Y1 and Y2. In this case, both Y1 and Y2, of course, are equal. If I were to take the takeoff point and move it before, so I'm tapping it off, so Y is now coming from here. In order to get back Y2 at the output, notice X goes through H before it comes to Y. So in other words, Y2 is X multiplied by H. So if I move the takeoff point before, in order to get the same thing coming out, I have to put in a block here, which is the same H, right? In other words, if you move a takeoff point before a block, then you have to add an additional block with whatever the transfer function inside of there was. Following me? Yes, no, maybe? Yeah? Good. Repeat the last part. Okay. So you look carefully at the diagram. If I take, notice that Y is X H, right? Forget the S for the time being. Y2. If I take this takeoff point here, right, and I move it to here now, right? So what I have, right? So move this a little bit. So this is what I have. If I move the takeoff point to before the block, in other words, I want to change its location, then in order for my y2 to be the same answer, y2 is x by h. So I must put in another block here with an h in it. Right? So y2 still remains its value. In other words, if I move a takeoff point before a block, then I have to add another block that has the same transfer function as the one I'm moving past. Fair enough? Good. So here's the other, well, obviously, if you move to the right, then you can also move to the left. So if I take a takeoff point and move it after a block, in this case, y is equal to x at this point. So if I take the takeoff point here and connect it after the block, if I have this scenario, then x has gone through h. So right now, if I leave it like that, I have xh coming out as y2. So in order to avoid that, I have to divide by h. In other words, I have to put in a block here whose transfer function is 1, or the inverse of the transfer function that I moved forward across. Yeah? So when you move before a block, you have to put in a block that is the same as the transfer function. And if you move after a block, you have to put in an additional block that is 1 over the one that you're bypassing. Yeah? Just the opposite, but you simply, you figure it out by watching the particular output at as it happens. Okay, so that's blocks. What about summing junctions now? The first one is takeoff points, right? A takeoff point is like you take a wire and you splice another wire into it. That's fine. What about a summing junction? The summing junction now, so I'm taking this junction here and I'm going to move it before the block. Again, you look at what happens. A summing junction is taking two signals and adding it together or subtracting it. So ys, for instance, here, let's call this z just for argument's sake. Ys is equal to z minus v. Yeah? If I take this entire block and move it here, right? X is still going through, so y at this point in time will still be getting the excess hs part. That is fine, but it still has to, we still have to find a way of getting this bit in. So to do that now, if I move this before the block, I have to multiply vs by 1 over h, so that when it goes back through h again, vs over h multiplied by h gives me back the v. So I'm back to the z minus v again. Right? Seeing that? If you take a summing junction and you move it before a block, then you have to add an additional block to the summing junction, going into the summing junction, whose transfer function is 1 over the block that you just bypassed. And of course, naturally, if I take the summing junction and I move it from before to after, take this and move it after, then Remember, this summing junction has an input coming into it. The summing junction, when you move the summing junction, you're moving where the input to the summing junction is coming from. So if I move it here, Vs goes in here and is multiplied by Hs, and of course added to whatever excess is. So if I take the summing junction and move it afterwards, then V has to be multiplied by Hs before I add it back to the summing junction. Because by moving it here, I bypass this, so I have to put it back. Make sense? Notice this is the opposite of the takeoff points, right? So you could remember it that way. If you're having difficulty remembering, work out one, and then the other one is now the opposite. But you figure out by looking at what happens to the signal, right? If I move a takeoff point before and after a block, or if I move a summing junction before and after a block. So let's apply that to an example and see how it works. So here's that one we started the class with, and we have some transfer functions for GH, for the two G's and the two H's. We're not going to worry about that as yet. What you do is that you simplify the entire diagram, and then you make a substitute for G and H. Right? So you look at the diagram and remember, for many diagrams, there is more, or there are more than one correct, there is more than one correct way to find the solution to it. So I may look at something and you can see something totally different. The issue is that once you move around, then you just follow the rules that we just established. So let's look at this one. We started it off and we said, all right, that this block here, is almost the normal two-block feedback, except for a takeoff junction here. So let's see if the first step, move the takeoff junction, take this and move this out of the way. So we take this takeoff junction and we move him out of the way. Right? So we connect him back. Sorry, it shouldn't have an arrow on it. Right? So we want to take the takeoff junction and move it out of the way. What do I do? If I do that, so this is what I'm doing. If I do that and move it out of the way, then I could now apply that positive or negative feedback rule that I know. So if I move the block out of the way, I'm moving a takeoff junction from before a block to after a block. So that means I have to insert something here. What is going to be in there? Right? Notice what happens. H is a feedback block, so H is coming here. Right? Right, there we go. Good. So H is taking off here and is coming into, or the signal going into H, sorry, is coming before G2. So if I move the takeoff pointer after G2, it means that whatever is coming out here going back has been multiplied by G2S. So what I'm going to have to put in here, as somebody just said, is 1 over G, or 1 over G2. Yeah? Make sense? Yeah? No, maybe? Right. So now we could zoom in. Let's zoom in a little bit. So now we can tackle this. And what is that? That is my normal feedback loop. It's a negative feedback loop. is drawn upside down. So what is the transfer function of that in blue? We did that yesterday. In fact, yesterday was the fourth time I think we did it, as I mentioned. So you can now simplify that, and that is going to be G2 over 1. There's negative feedback, so that's plus or minus. Plus, right? So negative feedback, very good. Right, so G over 1 plus G2H2. So you can simplify that so that, forward a couple of slides, and this is where we are now. So what next? Well, we have, if you look at it, we have this block here, right? Potentially, except for this. So what we need to do is to relocate this line here. So let's get that out of the way. We're going to take this and we're going to move it beyond the takeoff point here. Now, just as a little aside, if I have a line like this, with a takeoff point here and a takeoff point here, this is A and this is B, right? So they're going in different directions. These are not summing points. So takeoff points means information being fed back. This is the same. If I draw this on a line, I could, if this is so in a diagram, I could redraw it like this. I could put B here and A here. I haven't changed anything. Fair enough? So you can always separate takeoff points, and sometimes you see this happening in diagrams. They'll put one takeoff point and they have B and A. You could separate this into two, just like this. So manipulate them a little bit. What I tell students as well too is to, when you're doing this thing, get plenty paper. Right, so you don't have to, if it's scrunched up and you're trying to draw the diagram too small, sometimes you might miss that. So we're going to take him and move him to somewhere about there, right? So that when we do that now, we then have this big block to deal with. So if I take that and I move that line before here, I'm going to have to add a block. So the takeoff point is moving from before to after the block. So what am I going to have to put in inside of here? I'm going to have to put a block. Well, let me just draw it here. Right? Exactly. It's going to be the inverse of what we have. Right? So if this was a big X here, if this was a big X in the block, the takeoff point has come before. So if I move the takeoff point to after, right, the takeoff point here is being taken off before it was multiplied by X. So if I put it after, then I'm going to have 1 over X, whatever X is inside of there. Right, so you're beginning to follow. Right. So we're almost there. We've done a, let's just back up here a little bit. So I've also combined these two. These are two cascaded blocks, right? So this is, you could combine these two now into one. So kind of did two bits of simplification. Don't do too much on one diagram. It's always good to simplify or do one process per change on the diagram. Yes, you sometimes have to redraw the diagram, but use pencil and eraser, don't draw it in ink, and write clearly. Sometimes I myself am doing solutions or exam questions, and you come up with the solutions, and you copy some of the things incorrectly, sorry. So like here, might have had, you know, if you don't copied it correctly, might have H2 over G2 or H1 over G1 for some strange reason, right? But so be very careful and just watch it carefully. All right, so we simplify this now. We simplify this. We combine these two first before we simplify it. So this will now be, it's a cascade, so it's G1, G2 over 1 plus G2, H2. So that's a forward block. This is the feedback block. So it's going to be this. It's a negative feedback block. So it's going to be this over 1 plus this by this again. Do that. Combine them up, and this is what you have here. So we're almost home. What about this now? What does that look like? Right. So this one, you can consider this line. Oops, very socky here. Hold on. You can consider this line as a block with a weight of 1. Right, so if you want to imagine it, we have a block going here, right, and you have something coming in here. This is a summing junction. So this, if I were to simplify that entire, this little loop here, this loop here now, right, is 1 plus G2H2 over G2, right? So a straight line is just a connection with a block gain, or a block or a function of 1. All right, so this is 1 plus that transfer function there, no multiplication involved. So do that. This is what we have. And of course, the last step is to multiply this, multiply by that. Right, so this is the final transfer function here. All right, and then of course the final simplification that you will do, and you all can try this after you experiment a little bit with this, is to substitute for G1, G2, H1, and H2. And that gives you now the proper transfer function for whatever that block was. When you're simplifying, you shouldn't have any fractions inside of here. So when you're doing this kind of thing, don't leave the answer where you have like a G2 over H1 somewhere inside of here. You multiply everything out. Okay, and yeah, somewhere inside of here you shouldn't generally get any strange numbers appearing. Occasionally, depending on the constants on the in the system, you should get it. And of course, you shouldn't usually get in a real system, you shouldn't get anything like H1 squared or G2 cubed. You shouldn't get blocks to the powers. Not normally. In a real system, you wouldn't get that. Maybe in questions, just to see if you know how to manipulate blocks and get some sort of answer, it might turn up. But usually, just bearing in mind, if you later on, like when you're doing your controls, or if you're block diagramming out for a design of some sort, and this will occur, this occurs in other courses as well in level 3. Remember that if you get something squared and powers to the blocks, something went wrong in the either the model or in the simplification of the diagram. Yeah. So make sense? right? You have to try it. Yeah. So this is where we started. Now that was one approach. There may be other approaches that you could take. So for instance, right, if you look at it, I could take this line here. And if I were to take this, it might make things more complex sometimes depending on the choice. So if I make this and drop this line here, right? So if I do that, does that help me in any way? Let me see. Right, if I take this out of here, right? Now I could look and now have this. No, I still have the same sort of thing. So if I move that out of the way, that wasn't helping me that much. Let me see. What are the possibilities? We have to start simplifying early. Right? One of the manipulations you can't do, you can't swap these. So you can't change the order of summing and takeoff points. Remember, summing junction, two functions are coming in to be added or subtracted. A takeoff point is just sharing the information back. It's a takeoff point, so it's a feedback point. So you can't really swap the two of them. You can interchange the order of a summation or a junction. I just showed you that, right? So you could also, for summing junction, if you have a summing junction like this, right? So you have A, you have B. So this is plus, and let's say plus, and then you have C coming in. This is here, right? Remember that A, in this case, plus B minus C, right, is the same as A minus C plus B, okay? Is the same as B minus C plus A. So you could manipulate summing junctions quite a bit if they happen to be next to each other, or well within reasonable distance. Or if you move a summing junction, from some place to another place before a block, you're allowed to do that. Then you could swap the positions of the summing junctions fairly easily. Right, so let me see. I'm trying to look and see if there was any other. There possibly are. If I were to take, I'm still constrained here, so it might be possible to move the line, this line out of the way, right, which is our first thing. Actually, this one doesn't seem to have too many options on it, but there are others that usually would have more than one option. This just had 4 blocks in it. So for instance, if we were to look at this one here, so this is a homework example that you could have a look at. Let me just zoom it up a little bit. Right, so same sort of process. Here's one of those, right? Here's one of those where the two summing junctions are next to each other. So you could probably see what sort of manipulations you are able to do with this one. Try this one. I have the solutions for it. Right, there are some things. Remember, you want to get the feedback block, a positive feedback or a negative feedback block. You want to be able to manipulate everybody to get it into that thing, one little unit at a time. Right, so this one, right, for instance, if you take just and you move this out of the way, then you have G1, G2, G3, and H here that you could play around with. All right, and then after that, you could then probably simplify. It looks like you have another feedback loop and then another feedback loop. So it's almost like a nested set inside of here. So try it. It's not that difficult. All right. So any questions on this type of block diagram on the simplifications? Simulink in MATLAB allows you to draw out block diagrams of systems and describe the internal functions of each block, right? So it is a way of very complicated systems of mapping it out and getting certain types of responses in it. All right, but it's always useful to double check what is being done. So let me see. Say the other comment there. Can I do this? G2 by G3. G2, G3. After moving the line. Yeah. Right, yeah, you have to move the line first, and then you have the G2, G3 over 1 plus, is negative feedback here, 1 plus H2, G2, G3. Yeah, exactly. Right, so you shift that, and then you simplify it, and then you'll get a block within a block to take a simplify again, it seems. Yeah? All right, so let's have a look at a little variation of this now. This now is an incident, sorry, a situation where you have a disturbance coming in. Now, this is something that you will encounter quite a bit in your controls as you go through. So here it is. If you, most systems, most control systems and most electronic systems work nice and well, and we tend to ignore this bit here, right? So the system has two blocks, and you have the controls there and so on. And how this is modeled is that you have a controller, and you learn all about those terms in subsequent courses, right? You will meet it next year in 2009, and then it crops up again in things like energy systems and further controls as well. So you have two things. You have a plant, which is an industrial plant, so some sort of thing, and it boils down to a block here. This will be, this inside of here is a whole system comprising of many other blocks and subsystems as well. So this is just an overall summary of the entire plant. And the plant does something, and then you have a controller block. Now the controller block is where the inputs from the user comes in. So the user sets certain things, like if you're making methanol, for argument's sake, it will set the flow rate for natural gas. It will set the temperatures for the pressure chambers. It will set the flow rates for liquids coming in and out of the mixing vessels and the like. Pump speeds, therefore, to cope to that, valves to open and close and shut and the like. So it is set, and the information from the controller goes to the plant. You remember yesterday we were talking about signaling and the kind of information that will go from one point of the plant to the other. That was it, when we were discussing certain types of things, like I think it was mentioned the 4 to 20 milliamp and those kind of things. Just think about if you have a plant that is occupying an area of maybe a square mile. So there's somewhere in a control room, somebody sets something. Now that set value has to communicate to something in the plant, and it goes across some wires. But a lot of stuff happens in the wires. We just had a lightning flash up by me. That would send a lot of noise, which is little voltage spikes on the signals that going from one point to the other, and the system has to be able to cope with that. So how we model that is by putting in another input that may happen along the way, and we call that a disturbance input, that is D here. So how do you simplify a diagram like this? You have two inputs basically coming in, and one of them is the real input. This is the real thing that we want, and this is the other one that happens incidentally, but we have to cater for it, right? The lightning, the voltage spike, the loss of a signal, for argument's sake, a malfunctioning device, all of those things. So we've taken a system and we reduced it to two sets of blocks. One is a whole control system inside somewhere, and one is a whole plant outside somewhere. And now we've inserted this extra summing block inside of here. And I want you to think about it, right? And there's an answer on the next slide, which you which you have. But what I need you to do as part of the exercise for this is to look at this and use superposition. Remember, we're dealing with linear time invariant systems, so we can use superposition. Superposition means I can take one input at a time and work out what happens and then add up the solutions to get the final answer. So you're going to look at this block diagram here, and then you're going to see if input alone, if input RT alone is there, what answer you get, and if input DT alone, what answer you get, and then add up the two. And if you did that correctly, you're supposed to get, well, here I've actually controlled it to the, put it back into the Laplace domain, really. Look at this thing, take RS by itself and DS by itself, and then show that the answer for that system is going to look like this. Notice that the output here is a function of two things, the disturbance and the real, what do you call it? The real input that I want. And I could see if, for instance, now if I have that, if DS is a step change somewhere that happens, or if RS is a step change and DS happens to be a sinusoid, what will happen to the system? How will it respond? Will it oscillate? Will it overshoot? Will we have, those behaviors that we look at, right? So your homework on this bit is to look at this using superposition, taking one input at a time and adding it up. Look carefully at the diagram and see if the answer that you get looks like this. If not, well, then maybe I'm wrong or you're wrong, and we'll talk about it in a tutorial session. We'll come back to that because the solution for this will be in a tutorial. So, questions? That has nothing to do with block diagrams. Yes, your midterm is on Tuesday, the 2nd of November. Right? 1 p.m. thereabouts. So any questions related to block diagrams? It's like many things that we do, it is theoretically, in fact, not theoretically, it is I said about questions about block diagrams. It is conceptually fairly simple. Okay, moving the blocks around and shifting them around is conceptually fairly simple. Once you remember the four things that we spoke about, moving a takeoff point before and after a block, and moving a summing junction before and after a block. You cannot swap takeoff points on summing junctions. You can swap the position of takeoff points together, and you can swap the positions of summing junctions together once they don't have a block or another takeoff point between them. All right? Once you remember the four basic rules, then you're all right. Stephen, you said fine for R alone, then D alone, and Adam. Yeah, I was saying that you use superposition for this. So superposition, because we're dealing with linear time invariant systems, mean we can take it one input at a time. So let one input be 0 and let one input be whatever it is. And then let the other input be 0 and go back to the first one, and then see what answer you get. The answer should look like this one here. Yeah? All right. Okay, so this is the end of part 1. Let me stop the recording.